Hello students, today I am going to discuss the properties of S block elements, in which we will study about the ionization energy. So let's discuss the ionization energy of S block elements. Ionization energy. So comparing alkali metal and alkaline earth metal. So we know the configuration of alkali earth metal NS1 and alkaline earth metal is NS2. So lithium, sodium, potassium, rubidium and cesium. In case of group 2 alkaline earth metal, beryllium, magnesium, calcium, strontium, then barium. We know that when we move top to bottom, the size increases and ionization enthalpy decreases. In case also size increases, ionization enthalpy decreases. This is our general characteristic about the alkali metal and alkaline earth metal. When we compare the first ionization enthalpy, the first ionization enthalpy alkali metal is less than first ionization enthalpy of alkaline earth metal. First enthalpy of alkali metal is less than the first enthalpy of alkaline earth metal. But when we talk about the second ionization enthalpy, so let's discuss the second ionization enthalpy. For example, sodium and magnesium. Sodium, the outermost configuration is 3s1 and their outermost configuration is 3s2. So when sodium lose one electron, it becomes sodium ion and their configuration becomes 2s2 and 2p6, and their outermost configuration after losing one electron, 2s2, 2p6 and 3s1. So this is their first ionization enthalpy. First ionization enthalpy. So first ionization enthalpy IE1 of sodium is less than magnesium. Sodium is less than magnesium. But when we talk about the ionization enthalpy of second ionization enthalpy, in that condition sodium has greater ionization enthalpy than magnesium. So how it is possible? So let's see here. After losing one electron, sodium ion acquire noble gas configuration. There is a full-filled p orbital. But after losing one electron, magnesium has one electron in their outermost orbit. So there is less energy required to remove one electron from this orbital in comparison to one electron from the full-filled p orbital. So the second ionization enthalpy of sodium will be greater than the magnesium. So after losing one electron, alkali metal will attain a more stable noble gas configuration. So in that condition, the second enthalpy of sodium will be higher than the magnesium. So Let's we discuss the second, third, fourth property, that is metallic nature. Metallic nature. We know that metallic nature is inversely proportional to the ionization enthalpy. Metallic nature high, ionization enthalpy low, ionization enthalpy high, metallic nature low. So as we know, ionization enthalpy of alkali metal is less than ionization enthalpy of alkaline earth metal. So alkali metals have greater metallic character, than the alkaline earth metal, due to their low ionization enthalpy. And alkali metals are more electropositive in nature, so that alkali metals are more electropositive in nature. The next property is the crystal structure. Alkali metal and alkaline earth metal. Alkali metals all are BCC, means body centered cubic structure. Body centered cubic structure. It is the less close packing. In fact, we will discuss about this structure in class 12, but here I am introducing the type of crystals of the particular S block elements. So the alkali metals are body centered cubic like structure, but in case of lithium at low temperature it exists in hexagonal close packing structure. Hexagonal close packing structure. In class 12 solid chapter, all are given in the particular chapter. And HCP is more close packing than the BCC. It is the more close packing. Why sodium is soft, potassium is soft, and other elements are hard? These all characteristics depends on their structure, their lattice structure, their crystal structure, how they are packed in their lattice form. So alkali metals are mostly BCC in structure. Lithium only, except lithium at low temperature, it exists in hexagonal close packing, which is more close packed structure. In case of alkaline earth metal, so beryllium and magnesium is HCP. HCP, hexagonal close packing. So HCP, hexagonal close packing. So it is the more efficient packing, as we discussed. More efficient packing. More efficient packing. In case of calcium and barium is the face centered cubic close packing. Strontium is BCC. Due to large size, less efficient packing. About the strontium, due to large size, less efficient packing. Efficient packing. So this particular HCP and FCC is more efficient packing in comparison to BCC. So suppose this is suppose crystal lattice, this type of arrangement takes place in their crystals. So strong, very close to each other, this type of arrangement, so strong metallic bond and high lattice enthalpy. Due to this type of arrangement, more strong metallic bond and more strong metallic bond, so their lattice enthalpy must be high. So high lattice enthalpy. So all these terms are given in your chemical bonding chapter. Metallic bond, what is metallic bond, what is lattice enthalpy. So go through these terms are not new for you people. So this is the reason the alkali metal group members are soft and ductile, and their low melting point and boiling point and low density, low lattice energy. So this all are depend on their structure, because these are exist in the body cubic center, means less efficient packing, and they are more strong packing. So alkaline earth metal show more efficient close packing, more efficient close packing than the alkali metal, So therefore these are hard and brittle, high melting and boiling point, high density, and high lattice energy, So the next property is the melting point and boiling point on comparing group 1 and group 2, means alkali metal group and alkaline earth metal group. So melting point and boiling point. So alkali metal group, alkali metal and alkaline earth metal. So on moving down the group, as we know, size increases, packing of lattice decreases, so melting point and boiling point also decreases. So lithium, then sodium, then potassium, then rubidium, then cesium. This is the melting point and boiling point order. But in case of alkaline earth metal, trend is irregular. Their melting point trend is beryllium, then calcium, then strontium, then barium, then magnesium. This is the melting point order, and their boiling point order is beryllium, then barium, then calcium, then strontium, then magnesium. This is due to their structure. As we discuss about the structure, crystal structure, so their melting point and boiling points are irregular, not regular like alkali metal group. Let's we talk about the flame coloration. Flame coloration. Due to high ionization enthalpy of alkaline earth metal, beryllium and magnesium do not impart color to the flame test. As we know, electron present in the ground state. Suppose this is the ground state and this is the higher state or excited state, and the electron present by absorbing energy jump to the higher state. When it come back, it release different wavelength. So it radiate energy of different wavelength. So we can see the different color of the group 1 and group 2 elements. So alkali metal group, lithium show crimson red color, sodium show golden yellow color, and potassium shows violet, rubidium shows red violet, and cesium shows blue color. It absorb energy and get excited state, when it come back, so it release or emit different radiations of different wavelength. Alkaline earth metal. Beryllium and magnesium do not impart color. Beryllium and magnesium do not give flame test due to high ionization enthalpy, as we have discussed already. Calcium gives brick red color, brick red color. Strontium gives dark red, and barium gives apple green color towards the flame test. Apple green color towards the flame test. Let's talk about the hydration energy, hydration of ions and hydration energy of S block elements. Hydration of ions and hydration energy. When the salt of the group 1 or group 2 dissolve in, suppose Mn plus, dissolve in water, the water molecule surrounds like this. Because alkali metal or alkaline earth metal is a positively charged and water molecule in which oxygen is negatively charged. So there is a force of attraction exists or develop between this positive charge cation and the negative charge of the water molecules, and during this process the bond is set up and energy released. So force of attraction developed between metal ion and the water molecule, and energy release is known as a energy release is known as a hydration energy, and this process is known as hydration of ion, and this process is known as hydration of ions. So hydration energy is charged by size. So hydration energy is inversely proportional to the size and directly proportional to the charge. So this is the relation between hydration energy and charge to the size. Alkali metal. Hydration energy. The highest hydration energy, lithium ion, then sodium ion, then potassium ion, then rubidium ion, then cesium ion. And alkaline earth metal. So beryllium ion, then magnesium ion, then calcium ion, then strontium ion, then barium ion. So this is the reason when lithium form lithium ion, the outermost component 2s1, here their s orbital becomes empty. So 2s and 2p, 2s and 2p. So water molecules formed coordinate bond. Water molecules forms coordinate bond with this lithium ions and form the 4 coordinate bond with lithium ion, and their hybridization become sp3. So this exists in the lithium with 4 lithium H2O 4, their coordination number is 4 and the positive charge here. Positive charge. This is the oxidation number of lithium. So lithium exists in the nature in the hydrated form. This is the hydrated form. So when we talk about the alkali metal, only first member, the lithium, can form the 4 coordination bond because it does not exceed their coordination number more than 4 because it has no empty orbital like other member have sodium, potassium, rubidium, cesium. Sodium, potassium, rubidium and cesium. In case of sodium, potassium and rubidium, cesium, so see sodium ion, potassium ion, rubidium ion and cesium ion. It can suppose the configuration is 3s1. So when sodium ion forms, so 3s, 3p, and in the third shell d orbital is also present, 3p, and it is the 3s. So by taking 6 orbitals, it forms sp3 d2 hybridization. 6 water molecules form the coordinate bond with sodium ions. So the formation of compound like this, and the oxidation number is this. So coordination number becomes 6, means only 6 water molecules can form the coordinate bond with sodium of this particular orbital. So 6 water molecules form the bond with sodium ion in the by the coordinate bond of this particular empty orbital. During hydration of water molecules, during hydration of water molecules, during hydration water molecules donate electron pair to vacant orbitals of metal ion to form coordinate bond. Due to non-availability of vacant orbitals, lithium can only bond with 4 H2O molecules and exist as lithium hydrated form. Whereas other alkali metals due to presence of vacant orbital, coordination number increases. Vacant orbital coordination number increases to 6 and they exist like this. So that's enough for today. Thank you. In the next video we'll discuss the next topic.